Hi, my name is Roshni Suresh, and I'm a current student in the NCSM online program. I'm in the Mentorship 1 program, where I conducted research at Dr. Jonathan Viventi's lab at Duke University, mentored by Alex Wright. I studied polydimethylsiloxane and encapsulation stability for near-field communication stickers in simulated use. Neuroelectrodes are small devices that interface with the nervous system to record or stimulate neural activity. However, neuroelectrodes can degrade for several reasons, including oxidation, corrosion, wear, fatigue, and material breakdown. In the Viventi lab, neuroelectrodes play a crucial role in identifying the part of the brain where seizures occur, known as the epileptogenic zone. Polydimethylsiloxane, commonly referred to as PDMS, is a coating applied to these neuroelectrodes. These coatings enable the device to withstand several conditions found within an organism's body by protecting it against biodegradation. Rather than using neuroelectrodes, which are limited in supply and expensive to produce, near-field communication tags, known as NFC tags, were used to test the effectiveness of PDMS. These NFC tags are used for everyday applications, including contactless payments and smart home automation. My research question is, how long can PDMS protect wireless NFC tags from solution ingress and functional degradation under simulated long-term use conditions? The objectives of my research are to create molds to encapsulate the NFC tags in PDMS, learn and apply PDMS mixing, pouring, and degassing techniques, use an aging setup to stimulate long-term use, and analyze changes such as physical integrity and performance over time. For my methods, I used 4 different NFC tags, and there are 2 different aging tests, namely accelerated aging and reactive aging tests. For the PDMS was created by combining the PDMS with a curing agent, placing it in a vacuum chamber until the entire formula was degassed, meaning no bubbles were remaining, pouring the PDMS into the mold with a sticker, cutting the sticker out, and then putting the halfway encapsulated sticker into the larger mold. Then, this process was repeated for the second half of the same NFC sticker. For the accelerated aging test, 2 tests were conducted, a regular accelerated aging test and a reactive aging test. The reactive aging test incorporates hydrogen peroxide. Hydrogen peroxide represents reactive oxygen species, known as ROS. These are molecules that contain oxygen that are naturally produced in an organism's body, particularly by immune cells, to fight off viruses and foreign invaders. ROS, however, may cause the devices to deteriorate. As such, it is crucial to add hydrogen peroxide to an RAA setup to simulate the natural degradation of materials. The accelerated aging test does not include hydrogen peroxide, in which 1 day inside an accelerated aging test equals 32 simulated days inside in vivo conditions. The glassware was placed inside an autoclave, which kills harmful bacteria and viruses. Then, phosphate buffered saline, known as PBS, was combined with the hydrogen peroxide, which was when necessary, and the PDMS encapsulated tags were then put in the jar. For the accelerated, both these setups were placed in the oven. However, the accelerated aging test was set at 87 degrees Celsius, in which 1 day equals 32 days in vivo conditions. The tags were tested for their durability by placing the jars on a signal reader and assessing how they degraded over time. When the signal reader could no longer find the sticker as it was paired to it, it means the PDMS encapsulation has degraded, allowing this liquid to seep into the encapsulated layer. Of the 4 tags placed in the aging setups, only 1 sticker, namely tag 2, had failed quickly. Tag 1 did not fail, but tag 3 and 4 failed after prolonged periods of time. Following further analysis, tag 2 had failed due to improper laboratory technique. As the images show, tag 2 had an evident cut in the PDMS encapsulation, providing a clear entry point for the liquid to seep into the sticker. Tag 3 and 4 had failed due to degradation. Due to the limited number of trials, a definite conclusion cannot be reached, but preliminary results suggest that PDMS can provide a moisture barrier of up to 1.5 years for in vivo simulation. Hence, PDMS has the potential to serve as an effective encapsulation layer for wireless electronics in the brain. This has potential for real-world application, namely neuroelectrodes and wireless electronics placed in the brain. Future directions include increasing the number of samples tested in the 2 setups, reducing the mold size to assess any potential effects, and extending the testing duration. I'd like to thank the NCSM Foundation, the Burroughs Welcome Fund, the STRIP staff, and Duke University for giving me this wonderful opportunity this summer. Thank you.